Hello and welcome to our next lecture. In this lecture we will actually solve the heat equation that we derived in the previous lecture. The method that we're going to use today has a name, the method of separation of variables. This method is general enough to produce solutions not only for the heat equation but also for the wave equation and the Laplace equation, so you will see the applications of this method on quite a few occasions. This method is based on a few assumptions that we can make about the solution. First, we will derive a series solution, which means that we're going to derive a certain basis, and then the solution to this equation will be a summation of some coefficients times basis functions. I'm not specifying what are the limits of summation for n. They may be from 0 to infinity, from minus infinity to infinity, or say from 1 to infinity, depending on the case we're discussing. We're going to assume that each building block function u sub n of xt satisfies the differential equation with only the boundary conditions. We'll deal with the initial conditions later once we construct a series solution. In other words, the function u sub n of x of t satisfies the equation u sub n in partial derivative t equals kappa times u sub n xx, and the boundary conditions also apply. For example, we may have a zero boundary condition at end 0, or we may have zero flux, or we may have zero temperature at another end, or zero flux at another end, or any mixture of the two. Each one of those building block functions has a very special form. It's a function that is a product of a function that purely depends only on x times a function that only depends on time. So it is a function that can be written as a product of single variable functions. Not every function can be written like that. And this raises a few questions. For example, can we express all possible solutions in the form of these building block functions? Is it possible that some solutions will not have this form, and we will never be able to discover them this way? And the answers to these questions are no and yes. If we discover a solution in this form, then that will be the only solution possible, because the existence and uniqueness of solutions for these partial differential equations are actually well established. So if we have a solution in this form, that will be the only solution we can find. However, in certain situations, this assumption that the building block functions have this form is actually untrue, and we will never be able to use this method to find solutions for certain boundary conditions. So this method has limited applicability. However, the solutions that we get with it, if it works perfectly. So the method works this way. First, you need to obtain the form of the building block solutions, u sub n of xt. The form of these basis functions or basis solutions depends on boundary conditions imposed on the differential problem. After we figure out which functions constitute the basis for our solutions, we go ahead and compute the expansion coefficient c sub n. We do it by finding an expansion for the initial condition function f of x in the form of sum c sub n times u sub n of x comma 0. So at time t equals 0, the functions u sub n of xt become the functions of purely x. And if they constitute a basis, which most of the time they will, we will be able to represent the function f of x as this infinite summation. So here how this method actually works. We assumed that each solution is a summation of functions of the form x of x times t of t. Each function u sub n will have a different form of function x of x and t of t, but for clarity I'm not going to put an index on the functions x and t. If we plug this into the heat equation, we get that the time derivative of this product should be equal kappa times the second derivative in terms of x. Which yields, after a little bit of a manipulation, that x of x times the t prime of t, because that's the only function that depends on t on the left, equals kappa times t of t times the second derivative of x of x. So a little bit of manipulation, we can move all of the x's to one side and all of the t's to the other side. So we get these two fractions that should be equal to one another. And when we write it like that, it necessitates that each one of those fractions has to be constant. If it's hard to see right now, let me give you an example of a box that should contain apples and oranges. And then one person says that this box can contain only oranges, but there's another person who says that no, this box can contain only apples. And both of them are right. How is that possible? We know that this is only possible if the box contains no apples and no oranges. Then both of the guys are right. Let's look at these fractions again. The left fraction is a function of time only. The right fraction is a function of x only. How is it possible that one function that's only of time equals another function that's only of x? That's right. This can only happen if both of the fractions are just constants, because none of the fractions can depend on time or depends. Therefore, we can write that t prime over kappa t should be some sort of a constant, which I'm going to denote as minus sigma, and that should also be equal to x double prime over x. Why is this a minus sigma? Well, this is just a cosmetic preference, because frankly it doesn't really matter whether or not we put the minus sign on a constant sigma. And frankly, constant sigma can be also complex, but making it complex will not yield any solutions, so I'm only going to consider real values of sigma. Therefore, we obtained two ordinary differential equations. One reads that t prime plus kappa sigma t should be 0, and another reads that x double prime plus sigma x should also be 0. The form of the solution for each equation depends on what sigma is and whether or not sigma is positive or negative. And also which solutions we have to choose depends on boundary conditions. So we'll have to consider each case of each boundary condition separately. So first, let's consider the case when we have 0 boundary conditions. What does it mean for each function u sub n? Well, if u sub n of xt satisfies that u sub n at 0t equals 0 and u sub n at lt equals 0, that would mean that x of 0 times t of t should be always 0, and x of l times t of t should be 0. Well, if the function t of t is 0, then we have a trivial solution. U sub n equals 0. We're not interested in such trivial solutions. We are interested only in solutions that can be non-zero. Therefore, we assume that the function t of t is a non-zero function. And therefore, the only possibility for this to be true is that if x of 0 and x of l are both 0. Therefore, we have a differential equation for x function. And x should satisfy the boundary conditions x of 0 equals 0 and x at l equals 0. There are several possibilities for what kind of solutions we can get from a second-order equation. The first possibility is that what if sigma is 0? Then we get that x double prime should be 0. That means that x of x can only be a linear function. It's alpha naught plus alpha 1x. Okay, let's see how we can satisfy the boundary conditions. Plug in x equals 0. We get two equations. That 0 equals alpha naught plus alpha 1 times 0, and 0 equals alpha naught plus alpha 1 times L. If L is non-zero, this leads to the only possibility that both alpha naught should be 0 and alpha 1 should be 0. Therefore, we don't get any solutions that are non-trivial. Yes, in the case when L is 0, there are free variables in this linear system. But the case when we consider a rod of length 0 is kind of nonsensical and not very interesting at all. Another possibility is when sigma is negative. Because we will have to solve a characteristic equation, I'm going to introduce another variable. A variable lambda, and let's assume that sigma is negative lambda squared. Then we have a differential equation for x that has this form, that x double prime minus lambda squared x should be 0, x of 0 should be 0, and x of L should be 0. If you remember how to solve second-order equations with constant coefficients, you remember that you have to write the characteristic equation and find the solutions. And if you do that, you'll get that x of x is a linear combination of two exponentials, alpha 1 times e to the lambda x plus alpha 2 times e to the minus lambda x. Plugging in x equals 0 and x equals L yields the following system. We get that 0 should be alpha 1 times 1 plus alpha 2 times 1, and 0 should also be alpha 1 times e to the lambda L plus alpha 2 times e to the minus lambda L. If we consider alpha 1 and alpha 2 as unknown variables and assume that lambda is non-zero and L is not 0, then we will have a system that is consistent and whose matrix has a non-zero determinant, which means that the system has only one solution. And therefore the only solution possible is alpha 1 equals 0 and alpha 2 equals 0. And as a result, x of x in this case has to be a zero function again. The next possibility for us is to assume that sigma is positive. And again, because I will have to solve a second order equation, it is convenient if we assume that sigma equals some constant squared. In this case, the differential equation has the form x double prime plus lambda squared x equals 0. Again, x of 0 equals 0, and x of L equals 0. Using the characteristic equation to find fundamental set of solutions, we'll get that x should be some kind of a constant alpha 1 times cosine of lambda x plus the constant alpha 2 times sine of lambda x. Plugging in the boundary conditions will get us that 0 should be alpha 1 times cosine of 0 plus alpha 2 times sine of 0, which basically means that alpha 1 has to be 0. Plugging in x equals L will give us that alpha 1 times cosine of lambda L plus alpha 2 times sine of lambda L should be 0. But since alpha 1 is already discovered to be 0, we get that alpha 2 times sine of lambda L should be 0. And if sine of lambda L is non-zero, that would mean that alpha 2 has to be 0. And so it's impossible to get non-trivial solutions if sine of lambda L is non-zero. And x of x should be a zero function. However, if it turns out that sine of lambda L equals 0, then alpha 2 can be any constant. We assume that lambda is non-zero and L is non-zero. Therefore, the only possibility to get sine of lambda L to be 0 is for lambda L to be equal to some kind of multiple of pi. Therefore, lambda should be n pi over L. The function x of x therefore takes this form. And the constant sigma has the form lambda squared, so it's pi n over L squared. And here comes the question, what should alpha 2 be? Well, later on when we construct our series solution, we're going to multiply each one of the functions un by a coefficient cn, which is a constant. So cn multiplied by the constant alpha 2 will be just another constant. And since Cn are not yet established, we can incorporate alpha 2 into the constant Cn, or in other words, assume that alpha 2 is 1. So here's the phrase that mathematicians use in the situations like that. We say that without loss of generality, we can assume that alpha 2 is just 1, and therefore u sub n of x and t will be the product of function t of t, which we're about to find, times just sine of pi times n over L x. Now I think it's time to figure out what is the function t of t. For t of t we had the following equation, that t prime plus kappa sigma times t of t should be 0, and we didn't have any initial conditions on it. Solving this differential equation yields the solution alpha times exponential function minus kappa sigma t. Given that sigma is the square of pi n over L, we're just going to write it this way. It's minus kappa times pi n over L squared times t. Again, without loss of generality, we can assume that this constant is 1. Therefore, each function u sub n of x and t turns into e to the minus kappa times pi n over L squared t times sine of pi n over L x. Well, these are the building block solutions. So what about the whole solution? So summing up, we write u of x and t as a sum. In this case, we can see that n should go from 1 to infinity. Making n equal 0 will make lambda equal 0. Making n negative will only move the negative sign in front of the u sub n, and that will be absolutely redundant, because that would be the same function as the one that we obtained for the positive n. So n only needs to go from 1 to infinity, and we get Cn times e to the minus kappa pi n over L squared t times sine of pi n over L x. And here comes the final question. How do we determine Cn? Remember that we can express any function from L2 as a series of sines. U of x0 is supposed to be f of x, according to the initial condition on U. At the same time, this should be the summation, as n goes from 1 to infinity, of Cn times e to the 0 times sine of pi n over L x. This means that Cn is simply 2 over L integral from 0 to L of f of x times sine pi n over L x dx. It is simply the sine series for the function f of x, and once we obtain the coefficient Cn, we add up the functions and we get our solution. Let's look at a very quick example. Here we have the heat equation ut equals 1/2 uxx. We have the length of the interval is 2 pi, and then at both ends the temperature is 0. Also initially, this is the temperature distribution in our thin rod. So, what will be the solutions? Well, it looks like the solutions u sub n will be the functions e to the minus kappa is 1/2, so it's going to be 1/2 times pi times n over 2 pi squared t times sine of pi n over 2 pi x. Then the function u of xt will be the summation as n goes from 1 to infinity, c sub n times these functions u sub n when each coefficient Cn has to be turned as 2 over L, which is 2 over 2 pi, times an integral from 0 to 2 pi of f of x, which is x, times 2 pi minus x, times the sine of pi n over 2 pi x dx. I know the computation is going to be quite lengthy, so I'm just going to switch to Mathematica and do exactly that. And here's the setup. I have L defined to be 2 pi, f of x defined as x times 2 pi minus x. I compute the coefficients bk, because I copied the formula from my sine series, which is the integral of f of x against the sine of pi k over L times x. Then I just add the function bk times e to the appropriate terms times sine appropriate terms, and I add just the 20 terms. Well, here I'm defining the function u of xt to be that sum. Notice I don't use the column right here, and this is crucial because if I use the column, then the Mathematica will actually take a long time to work it out. So, but if I use just the equal sign, then the u sum is going to be evaluated, and then u would just be replaced with what u sum, with whatever expression is inside u sum. And then when I plot u of xt, that expression will be used instead of actually this sum being computed every time a point from this function needs to be evaluated. Let's see what happens. So at the time t equals 0, we have our function to be this parabola. And then, as time progresses, my rod cools off. Nothing very interesting. But let's see what's happening underneath the hood. Let's add not the first 20 term. Let's just add one term and see what happens. Well, now, it seems like nothing changed. But notice that this is not a parabola anymore. It is just a sine function. Term number 5. It's a small sine wave that also just kind of zeroes out very quickly. But it also plays its own role in the overall solution. So we can see that every single one of those functions actually plays a big role. So if I add the first 5 terms, I get a pretty good approximation of our solution. Can I have a temperature distribution initially that's not 0 at the ends? Absolutely. We can think about it as a situation as if we preheat the rod with a certain pattern, and then at time t equals 0, we apply a cooling device that keeps the temperature 0 at the ends. I can actually make f of x to be any function. As an example, we can try something like function unit step that turns on at x equals 0. Let's just say in the middle of the interval, let's say pi over 2, we step up. Then we step down. Let's say 3 pi over 2. And then finally we step down at x equals 2 pi. Well, first 5 terms do not represent the function quite well. So let's add a few terms. It's a little bit better. You can see what's coming. We start to have the Gibbs phenomena. So here's the representation of the function, as good as the signs can make it. So now, if I let t progress, we can very quickly see that the temperature evens out pretty quickly and this is to 0 as quickly as it can. The interesting stuff happens very early. So let's manipulate not for the first 20 seconds, but the first 2 seconds. So if I move it slowly, we can see that very quickly my temperature distribution becomes very smooth. That's really not a surprise. When you think about a rod that heated up, if you heat it up in this uneven pattern, when we have jumps, then it's quite understandable to see that at the points of jumps, the temperature will flow very, very quickly. And at the ends where the temperature is more or less constant, nothing will happen until the drops in the temperature reach them, and then the overall temperature will start decreasing. All right, let's look at another case. The case of the insulated ends. The boundary conditions here are slightly different. Let's see how the boundary conditions translate into the boundary conditions for x. If u sub n of xt should satisfy derivative equals 0, we get that the derivative with respect to x of x times t of t at x equals 0 should be 0, and the derivative with respect to x of x times t of t at x equals L should be 0, which leads, quite understandably, that it's the function x of x that should have a 0 derivative at 0 and 0 derivative at L, because t of t should be a non-zero function that should be unaffected by what happens with x. Just as before, we're going to consider 3 different cases. Case 1 being sigma being 0. This leads to the equation for x being x double prime equals 0, which again leads to x of x being alpha naught plus alpha 1x. Imposing the boundary conditions, we get that x prime at 0 equals alpha 1, and that should be 0, and x prime at L, that also equals alpha 1, and that should be 0. That means that x is just a constant alpha naught. And again, without loss of generality, we can assign the value 1 to the alpha naught. Since later on, we're still going to be multiplying this function by a constant c naught. In this case, the differential equation for t reads t prime equals 0. Therefore, t itself is a constant. And again, we can make this constant to be 1, which leads to u naught of x and t being just a constant 1. The second case is the case when sigma is less than 0. Just as before, we're going to assume that sigma is just minus lambda squared. And just as before, the differential equation for x reads x prime minus lambda squared x equals 0, with the boundary conditions that x prime of 0 equals 0, which is also equals x prime of L. Using the standard methods of solving the differential equations, we arrive that x of x must be alpha 1 times e to the minus lambda x plus alpha 2 times e to the positive lambda x. Plugging in boundary conditions, we get that x prime of x is simply alpha 1 times minus lambda times e to the minus lambda x plus alpha 2 times lambda times e to the lambda x. Plugging in x equals 0, we get that 0 should be alpha 1 times minus lambda plus alpha 2 times lambda. And x prime of L, which also should be 0, becomes minus alpha 1 lambda times e to the minus lambda L plus alpha 2 lambda times e to the positive lambda L. This is a system of equations for alpha 1 and alpha 2. Lambda must be non-zero, and unless L equals 0, this system of equation has a unique solution, and that unique solution is alpha 1 equals 0 and alpha 2 equals 0, which leads to a trivial solution x equals 0. Therefore, we must consider the last case, which is sigma being greater than 0. And again, just as before, we're going to assume that sigma is simply lambda squared. The differential equation now reads x double prime plus lambda squared x equals 0, with the boundary conditions being x prime of 0 should be 0 at both 0 end and end x will equal L. Solving the differential equation gives us the solution that x of x must be alpha 1 times cosine of lambda x plus alpha 2 times sine of lambda x. Plugging in the boundary condition requires us to evaluate the derivative, and the derivative is simply minus alpha 1 lambda times sine lambda x plus alpha 2 lambda times cosine lambda x. Plugging in x equals 0 will give us 0 should be x prime of 0, and that is alpha 2 lambda times cosine of 0 is 1, should be 0, which leads to alpha 2 being 0. Plugging in x equals L gives us minus alpha 1 lambda times sine of lambda L plus alpha 2 lambda cosine of lambda L should be 0, Well, we do know that this constant alpha 2 should be 0. Therefore, it just equals minus alpha 1 lambda sine of lambda L. If sine of lambda L is non-zero, this means that alpha 1 has to be 0, and therefore x of x is simply a 0 function. That's not an interesting case. A much more interesting case is when sine of lambda L equals 0, which leads to lambda L being a multiple of pi. Therefore, lambda is just pi n over L. And alpha 1 can be any constant. This leads to x of x being alpha 1 cosine of pi n over L x. And again, we can make alpha 1 to be 1, and therefore it's just cosine of pi n over L x. It means that sigma should be pi n over L squared, and therefore our solution should be a function t of t times cosine of pi n over L x. Now this is a good time to find out what t of t should be. The equation for t of t reads t prime of t plus kappa times sigma, which is pi n over L squared, times t of t should be 0. This leads to t of t being some constant alpha times e to the minus kappa pi n over L squared t. Again, without loss of generality, we can assume that alpha equals 1 is just e to the minus kappa pi n over L t. Pi n over L is squared. Combining all of these results, this leads to u of xt being a summation of the terms. So we have just c naught times 1 coming from case 1 plus the summation as n goes from 1 to infinity of cn times e to the minus kappa pi n over L squared t times cosine of pi n over L x. Lastly, we need to address the question of initial conditions. We know that initially u of x0 equals f of x, and that should be c naught plus sum as n goes from 1 to infinity cn times e to the 0 times cosine of pi n over L x. And we can easily see that is the same as the cosine series we derived some time ago for the function f of x. Therefore, the coefficients c0 and cn are found this way. c0 is simply 1 over L integral from 0 to L of f of x dx. And cn, for n being greater or equal to 1, it will be 2 over L, the integral from 0 to L of f of x times cosine of pi n over L x dx. And let's look at the example that's almost the same as the previous one, except that this time we make the derivatives to be 0. The constant kappa is 1/2, therefore the solution u of x t would be equal to c0 plus the sum of cn and going from 1 to infinity times e to the minus, this time kappa is 1/2, so it's minus 1/2 pi n over 2 pi t times cosine of pi n over 2 pi x. The coefficient c0 is simply the integral from 0 to 2 pi with 1 over 2 pi constant in front of it of the function x times 2 pi minus x dx. And all the other coefficients are 2 over 2 pi, the integral from 0 to 2 pi of x times 2 pi minus x times cosine of pi n over 2 pi x dx. Again, it's a lot easier to do this computation in Mathematica. Again, I prepared everything beforehand. Let's go ahead and evaluate. This is a familiar picture of the cosine series. We do see that the cosine series does not reach 0 at the ends, despite the function being 0 at the ends, because the cosine series tries to approximate with a function that zeroes out its derivative at both ends. I'm sure that if I add more terms, the representation is going to be a little bit better. As time progresses, this is what happens. All of the terms with the cosine are going to be decreased to 0 by the exponential functions. And the only thing that survives is the constant c0. So as time progresses, the solution converges to a state where all the temperatures are the same all the way throughout the rod. This makes perfect sense if rod is insulated from the outside environment at both the lateral surface and at both ends. The heat has nowhere to go and only heats up the cold places and cools down the hot places. But overall average temperature of this rod has to stay the same because the heat energy does not leave the rod. Just as before, we can also try to experiment with discontinuous functions. So I'm going to copy the function I defined before and try to compute the same approximation for it. So again, we need more terms to represent the function more or less accurately. And the ever-present Gibbs phenomena is showing up. If I increase T, we can see how the rod quickly averages its own temperature. Again, let's see what happens during the first few seconds. During the first second, the temperatures very quickly even out, and the sharp decrease in temperature is smoothed out by the process of heat conduction. So today we have seen how we can solve partial differential equations using the method of separation of variables. This method is the easiest to apply and use, but it has its own limitations. For cases with more complicated boundary conditions, most of the time people use numerical methods rather than try to come up with analytic solutions to these problems. In the next lecture, we're going to consider problems with mixed boundary conditions and problems where boundary temperature may actually be non-zero, and you will see that it introduces a few complications. For now, this is it. I hope you enjoyed the discussion, and I'll see you in our next video.